Hey everyone, I just want to welcome everyone joining in today. We'll get started in a few moments, just kind of allow everyone to make their way in. Thanks. All right, well, I think we'll get started with some introductions. Thank you all for joining us today. My name is Ben Chen. I am the Northern Director of the California Lake Management Society and also today's sponsor. So we're happy to provide these opportunities, these educational opportunities to the public. And today's topic is of personal interest to me. And we're very happy and excited to have Scott on board to give us a talk. So with that being said, we will get started with our sponsorship video. Again, Lake Tech is very proud to be a part of this, and we're happy to make this mission possible.
Lake Tech, a leader in aquatic resource management, provides innovative solutions to environmental challenges in aquatic ecosystems. They focus on sustainable management, helping clients understand and implement effective integrated pest management, or IPM strategies. Guided by the principles of IPM, Lake Tech has made significant strides in maintaining ecological balance in public waterways. Their expertise in a range of IPM tactics is instrumental in promoting healthier ecosystems in reservoirs and lakes. They harness the power of their proprietary management platform to closely monitor and understand the impacts of integrated pest management tactics on aquatic sites. Take, for example, this chart. It illustrates the change in dissolved oxygen levels throughout a water column when an aeration system is activated. A lack of dissolved oxygen can lead to using chemical inputs to manage algal blooms. But having access to this key data helps clients with optimizing management practices, ensuring both the health of aquatic ecosystems and the effectiveness of IPM strategies. At Lake Merritt, an urban estuary in Oakland, Lake Tech showcases their expertise with a pioneering initiative. In the summer of 2022, a red tide algal bloom resulted in a massive fish kill in the San Francisco Bay that had devastating effects on Lake Merritt's resident wildlife. The City of Oakland and the nonprofit Lake Merritt Institute approached Lake Tech for help in managing red tide algae using safer, more sustainable IPM practices. As a result, Lake Tech is managing a pilot oxygenation system designed to enhance the environment by providing waters rich in dissolved oxygen, essential for the thriving of aquatic life. This innovative approach directly tackles the challenges faced by the ecosystem, such as the risk of fish kills and algal blooms, by ensuring a healthier and more balanced habitat. Lake Tech's impact reaches far beyond the waters they help manage. By maintaining healthy aquatic ecosystems, communities can use and enjoy lakes and reservoirs for recreation. Access to these spaces, such as Oakland's Lake Merritt, is especially valuable in urban environments that can have limited natural recreation areas. And in such cases, social equity impacts are realized as one of the tangible benefits of sustainable pest management. Lake Tech's team is held in high esteem by peers and known as an advocate for responsible stewardship of water bodies. Their software and equipment is used by other lake management companies as well as government agencies across 15 other states. Eli Kirsch, Lake Tech owner-operator, has held board positions on regional and national professional societies, including 3 terms as president of the California Lake Management Society and 5 years on the board of directors for the California Weed Science Society. He is also a licensed agricultural pest control advisor in California. Lake Tech's application of integrated pest management practices has positively influenced waterway conservation, garnering recognition for their commitment. Their efforts towards sustainable aquatic ecosystems aim to ensure a healthier future for our waters, reflecting a dedication to ongoing improvement and stewardship.
All right, thanks everyone. So it is my pleasure today to introduce Scott Coffin. He currently serves as the pharmacokinetics research scientist at the Office of Environmental Health Hazard Assessment in California EPA, where he develops a novel risk assessment method to assess impacts of emerging contaminants with little to no animal toxicity testing. Dr. Scott Coffin previously served as research scientist with the California State Water Resource Control Board, where he performed research developing drinking water and aquatic ecosystem regulations for microplastics and other contaminants. Scott completed his PhD in environmental toxicology at the University of California, Riverside, and wrote his dissertation on plastic as a vector of pollutants in estuary and marine environments. Scott's expertise in data science, analytical chemistry, ecotoxicology, and risk assessment. Outside of his work, Scott can be typically found rock climbing, surfing, mountain biking, dancing, playing music, DJing, or spending time with his partner and other loved ones. Scott is a Wyoming native, but currently lives in West Sacramento, California. So thanks again, Scott, and we'll be happy for you to take it away from here. Thanks.
Thanks for the great introduction, Ben. Alrighty. So I'm going to give you all a bit of a Microplastics 101 presentation today. Some of you may have more background experience with this than others. So for those of you that do know a lot about it already, stay tuned because there's definitely some deeper cuts in here as well. So as Benjamin mentioned, I've been working on microplastics and plastic pollution for a while. Since I've been working in the field, I've seen a dramatic increase in the public's awareness of this issue. And I'm sure that you all see this in the news as well. It seems that everywhere we look for plastic pollution, we seem to find it. And I just want to take a big step back and really give you a bit of a perspective about how we actually got here with this awareness. And it starts really in our backyard. 1997, Captain Charlie Moore from Long Beach, California, took a ship out to the Great Pacific Garbage Patch. They didn't mean to be out there. Their sail broke and they needed to putt through the doldrums out there. But they discovered a surprising amount of trash that really was more like a soup of plastic than a island that may have been propagated in the media. But this is really the beginning of this field of investigation in modern times. And why do we care about this? As we all are familiar with these sort of hockey stick diagrams, plastic pollution, just like many other issues, are not going away. Under business as usual, it seems to be an exponentially increasing. Let's see, I'm going to turn off my video, reduce the bandwidth. Hopefully that's okay. Are people able to see my slides and hear me okay? Just want to make sure everything's going smoothly before I go forward. You could just get like a thumbs up or something. We'll take that as a yes. Okay. Be increasing exponentially under business as usual. Yes. Okay. Very good. Cool. That was seemed to be a bit of a delay for me. I hope that people are able to hear me well. So, in terms of where we're at currently, just to put this in perspective about how much plastic actually out there. In 2020, it was estimated that global plastic in the world currently outweighs all living animals by a 2-to-1 ratio. And this is not just plastic that is an outsourced impact of material in the world. It's also human-made stuff. Most of the world currently is made of human-made material, mostly buildings and infrastructure. Kind of a crazy statistic. So why do we care about plastic when it comes to marine management? One of the things that we're most concerned about is the degradation of these larger particles into smaller and smaller pieces known as microplastics. And this is a microbead in toothpaste that is taken, an image of it that is taken under scanning electron microscopy. So you can see here, one of these particles has many more smaller particles on the surface. And if we just zoom in even further to one of these small particles, you can see the formation of even smaller particles. So this is a great way to understand how one plastic particle can become millions, billions, and even trillions of smaller plastic particles. So what is the scientific universe doing about this? Luckily, there is a very wide increasing interest in the field, and there's currently estimated at least 10 publications coming out every day on microplastics. On the negative side, unfortunately, although we are seeing a lot more papers come out, we're not necessarily seeing better studies. And this is an analysis that I recently did for a comprehensive meta review of the toxicity literature of microplastics. And what we're looking at is the distribution of quality scores over time. And we don't really see an improvement in quality. So there's a lot of scientists getting into this field of study, but they're not applying the best techniques, which makes it difficult for us scientists that are trying to review this information. And really, it feels like we are maybe lost in a sea of information, not really unsure how to go forward. So there's a couple ways that journals are taking a stance on this. The Science of the Total Environment journal just released minimum requirements for measuring plastics and environmental samples, minimum quality criteria and reporting requirements. This is really a good step in the step in the right direction. And for anyone that wants to get involved in plastic pollution science, make sure that you are up to speed on what is considered the minimum requirements for quality of studies. Something else that we can't really depend on is the journal impact factor for providing good studies. There is a slight correlation between the journal impact factor and the total quality score that we're seeing. But as you can see here, there's a ton of variability. So just because a microplastic study is in a so-called good journal does not mean it's a good study. So just make sure we're all cautious and skeptical when we're reading these sort of buzzworthy articles that come out. I wrote a paper recently about this, about how we can get from this research level of investigation to something like regulations and standards. And I talk about in this paper the importance of harmonization, collaboration across many different stakeholders, standardization, targeted studies, and open science. So you can check that all out. It's in an open access publication in Environmental Science Advances. And my goal for that, and really for the work that I'm doing now, is to provide a little bit of an overview, a different perspective on this sea of information. Maybe we could be in a helicopter looking at this wave of information as opposed to just stuck in a boat in the sea and not really seeing the path forward. So all of that aside, I want to give you a bit of an overview about what California is doing about this issue. So there's really two bits of legislation that have driven all of the research from the regulatory agencies in California over the past 6 or so years. And these come from the California Senate Bill 1263, which deals with addressing microplastics in the marine environment, has some of these deadlines as shown here. And then also in 2017, our scientists looked for microplastics in tap water, finding it in 94% of samples in the United States and 83% of samples worldwide. And this finding prompted a very similar bill to Senate Bill 1263, known as Senate Bill 1422. And this is more narrowly focused on addressing the issue of microplastics in tap water. And so I'll also go into detail of how we accomplished all of these tasks shown here. So starting off, if you can measure the problem, then you can manage it. That's really a foundational theory to regulatory agencies and management organizations. But in the case of microplastics, we didn't have a standardized method. There's no EPA method. There's no other method available when this bill was passed. And we also needed a way to accredit laboratories to feel confident about results that we're getting. So we developed our own standardized method and evaluated its performance using an interlaboratory validation study. So we did this not only for drinking water, but more complicated matrices like ocean water, fish tissue, and sediment. And we did this using a couple of different techniques that use spectroscopy, Fourier transform infrared, or FTIR, and Raman. 26 laboratories from 7 countries participated in the intervalidation study. And I'll talk really briefly about the results. But first, just a really quick overview and actually how one would go about analyzing microplastics using our standardized protocol. This is a very simplified protocol. So basically, you would take a sample. If it's in a clean matrix like drinking water, all you really got to do is extract the particles.
Could anyone let me know if this is any better audio-wise? I've joined on my phone now. Cool. Alrighty. I'll take that as a yes.
That works.
Okay. All right. Sorry about that, y'all. Hopefully the slides are loading properly. Again, I had to join through a VPN. So, alrighty. We'll just go ahead and keep going. So, in terms of laboratory analysis, this is really the straightforward protocol here. And in order to evaluate method performance across labs, yeah, thanks for bearing with me, everybody. A little bit of troubleshooting on the fly. So in order to evaluate the laboratory performance of labs, we created blind samples, 4 different polymer types and size fractions, as well as some different shapes, just to understand how well these methods perform with different particle types. And really briefly looking overall at the results, this is a really complicated data set, but if you just take a big step back and look at how many particles were correctly reported or accurately reported across labs, you can see here that on this log scale, the median is 30%. So that means that laboratories are missing a lot of the particles that they should have been extracting and identifying, but that's really not the full story. And if we look at these different factors that we grouped the particles by, you can see that size is really the biggest determinant of method performance, laboratory performance. So the 1 to 20 micron fraction tends to be very poorly retained by laboratories, as well as very high variability. We also see some biases in the method towards certain colors and certain shapes as well. So this is by far not a perfect laboratory method, but we believe that it's good enough for our initial purposes of monitoring. We also evaluated how expensive are these methods and how much time do they take to run. And so we ran these, so we asked laboratories to report how long it took to run each sample, their costs for instrumentation and consumables. And what we found was that infrared and Raman spectroscopy are fairly comparable in terms of the accuracy and the time that it takes to run the samples, but Raman tends to be a bit more expensive. And so what you're seeing at these costs here, what that translates to in terms of a commercial laboratory running samples, most labs are charging about $2,000 per sample for this type of analysis. I'm sure that number is going to go down moving forward, but that's a general market price right now. So we have this method that is expensive and not perfect. And what we've learned from monitoring other environmental contaminants is that we don't necessarily need to use one method for every purpose. For those of you that are working on PFAS, you're probably familiar with some of these other assays that are used other than the targeted method using LCMS-MS. The top assay, for example, or total organofluorine. These get at different types of PFAS or different types of information. And so we applied that thinking to microplastics, and we came up with what's called a tiered monitoring framework, whereby most of the samples are going to be run using some kind of shortcut method, like just looking at total particle count or looking at plastic particles using a shortcut method like using Nile red. And we reserve this more expensive, labor-intensive method for just a smaller number of samples, just to really confirm what we're seeing. In terms of whether or not we can accredit this laboratories for this method, we have developed an accreditation program through the Environmental Laboratory Accreditation Program, or ELAP, through the State Water Board, to evaluate method performance and laboratory performance. Currently, we have 2 laboratories that have submitted packages to ELAP for accreditation, but we expect to see a lot more laboratories soon. So moving on a little bit to what to do with this information once we start monitoring for microplastics in drinking water. I'll talk briefly about the requirement from Senate Bill 1422 to develop a health-based guidance level. So in order to fulfill this goal, we convened a human and ecological health effects workshop with experts in the field on microplastics toxicology. And we charged them with answering questions about what dose metrics predict toxicity, what particle characteristics may be associated with more or less toxicity of these particles, what the adverse effects are in different organisms, and if we can come up with some sort of framework for developing a threshold for regulatory use. So real briefly, in terms of risk, we define risk as the combination of hazard and exposure, which is really comes out to a probability about whether or not it's going to cause harm in an organism. And so I'll talk first about assessing the hazard. Microplastics are an extremely diverse contaminant suite, and the hazards can be grouped into 3 different categories, including chemical-based hazards, biological, and particle. In terms of chemicals, we're really dealing with a cocktail here, with most plastics having many different types of additives. Some of them are known to be hazardous, and others we don't have information for whatsoever. And of the 10,000 known additives that are out there, about a quarter of them are already known to be substances of concern, and half of those are unregulated. When it comes to the biological hazards of plastics, we are learning a lot about the ability for plastics to harbor pathogens and exacerbate virus-induced mortality. A recent study found that when you expose a fish to microplastics in combination with a virus, it causes more mortality than just the virus or the microplastics alone. So this really could be a multiple stressor kind of contaminant that we're going to be dealing with. In terms of plastic particles causing toxicity, this is something that we believe to be fairly ubiquitous across different organisms and can affect these organisms through different mechanisms. And one of the key challenges in evaluating these hazard studies is that these studies are not exposing fish or rodents or other organisms to the actual plastic particles that we see in the environment. It's extremely difficult to do because we're really dealing with like a soup of plastic particles with different shapes and sizes and polymer types. And we call that a polydisperse mixture. In laboratory studies, they typically use just one type of plastic particle, like polystyrene foam or polyethylene fragments of a certain size. And so relating these two is actually quite challenging. One of the ways that we can address this discrepancy, though, is using what's called a toxicologically relevant metric. A toxicologically relevant metric is really a concept that has mostly just been applied to microplastics. And we have 2 effect mechanisms that we believe to be relevant for most aquatic organisms. One of them is very easy to understand. We call it food dilution. And here we're really only concerned with the volume of particles, how much space it takes up in the organism's gut. So let's say this bird here that's eating plastic from its mother, that plastic is accumulating in the stomach of that bird, and it's taking up space that could otherwise be taken up by food. And so they're not getting as much nutrient from food as they possibly could. When it comes to smaller particles that can accumulate in our organs, here we are concerned about the sizes of particles that can cross these barriers and really get into cells and tissue. And for here, we're concerned about the surface area of the particles because we believe the particles are interacting at the surface with these cells and causing toxicity. So now that we have a good idea of how these plastic particles are actually causing toxicity in organisms, we can apply what's called probability distributions based on size, density, and shape to align the concentrations that we're seeing in these hazard studies with those in the environment. And apologies for the slides. It seems like there's quite a significant delay between when I change the slide and when it shows up online, so I can see on my phone. So what I just mentioned here is really this broad overview of what our expert work group determined to be the main ways of understanding the microplastics hazard part of the equation. And we did a lot of research here and came up with some numbers and some approaches for moving forward, but we also identified a lot of research gaps. And if you want to learn more about what those research gaps are, we published this paper in a special issue of the journal Microplastics and Nanoplastics. Again, that is a fully open access journal. So to walk you through a little bit about how we actually applied our risk assessment framework for humans, we started with the available toxicity information from the literature, 29 studies, and then we screened these studies for experimental design, particle characterization, and applicability for risk assessment. So of those 29 studies, we were only left with 12 that were deemed to be usable for risk assessment, which then underwent additional expert review. We then assessed the reliability of each individual endpoint in those studies. And what we found was that the majority of reliable information that we had available was pointing towards impacts to the male reproductive system. We see consistent effects across studies on sperm deformity, sperm count, testosterone concentration, and a lot of other indicators of male reproductive harm. We've seen two reliable studies that point towards impacts to female reproductive success, and also some studies pointing at decreased body weight. We also found that the size of the particles really makes a huge difference for whether or not it can reach these reproductive organs. One study looked at particles ranging from 10 microns down to 4 microns, and they found that the smaller particles had a much higher probability of reaching the testes than these larger particles. And apologies for the slide, very significant delay that's happening. So what we did with all this information is we then applied a dose response assessment using EPA's benchmark dose modeling software. And here we were able to determine what levels the particles may be causing harm in these rodents studies, and see if we have enough information that we could potentially extrapolate this to humans. And so, as you can see in this figure here, we had fairly low variability across studies, as well as different particle sizes in terms of where we're predicting the effects to occur. So between 0.01 and 10 milligrams per kilogram day of these particles. And so if we were to compare where we see these, or where we predict these hazard effect concentrations to occur to the exposure that we see in the environment for humans, we would see a significant overlap between where we're seeing exposure and where we're seeing effect. But what's quite challenging with this comparison is that we don't have great understandings of human exposure based on what's in our food. So we have a really good idea of what is in our drinking water and in the air, and a couple of food items like seafood and beer and salt, but we don't really understand what is in our fruits and veggies, and especially what's in our packaged foods. And when it comes to packaging in particular, we believe that packaging may be responsible for a large part of our exposure. So One study found that when you open a water bottle, plastic water bottle, the shearing of the plastic particles around the lid creates microplastics that can then get into the water, into the air, and then you can ingest them on the order of 14 to 2,400 particles every time. Opening a plastic snack bag releases 14,000 to 75,000 microplastic particles. And if you really want to ingest a very large amount of microplastics, you would microwave something that's plastic that has food in it. So a study last year found that heating a polypropylene container filled with clean water for 3 minutes in the microwave released on the order of billions of microplastics and nanoplastics that were suspended in the water. And so if you really want to avoid exposure to microplastics, I would highly recommend not microwaving food containers that are made of plastic. So what did we do with all this information that I just showed? Our expert work group determined that we just don't have enough information right now to derive regulatory levels of microplastics in drinking water. This is because the effects database that we're working with is largely inadequate. We don't have a certain idea of how these microplastic particles are causing effects in humans. We don't understand the effect mechanisms. And we also don't have a complete understanding of the exposure of these particles. So there's very limited food data and no harmonized drinking water data sets available. So I want to talk really briefly about what we did for assessing the hazards of microplastics for ecosystems. Here we were dealing with a much wider data set. We had 167 studies with 117 species for toxicity data. Unfortunately, the vast majority of these studies did not meet our quality criteria for evaluation. So only 22 of the 167 studies were deemed to be fit for purpose, which also included data for 16 species. So basically 1/10 of the data set. We then went to further expert reviewing these studies and then aligning the data from these monodispersed studies to the polydispersed concentrations in the environment. And finally, using what's called species sensitivity distribution modeling to understand effects at an ecosystem level. So a species sensitivity distribution looks very much like a dose response curve, and this is used by risk assessors to understand where we might find effects in an ecosystem. We typically think about predicting the tail end of a ecosystem, like really looking at the 5th percentile of species that may be affected. And so we did this for microplastics, and we came up with a set of toxicity thresholds that we feel to be good baseline levels for assessing hazards to ecosystems. We did this not only for the effect mechanism of food dilution, again, plastics taking up space in the organism's guts, but we also did this for the more complicated tissue translocation mediated impacts effects. So where the particles are accumulating in the organs of these different animals. And so we came up with 4 different threshold concentrations based on where we would predict to see effects in sensitive ecosystems. One thing I'd like to show you about this data set is that we were able to, let's see, there is definitely a long delay between when I change the slide and when it shows up in your guys' screens. Sorry about that. We were able to build an interactive data portal for the toxicity information, which is entirely open access. This is called the Toxicity of Microplastics Explorer, or TOMEX. And as you'll see in a second, this application is meant to really be a user-friendly way to interact with the toxicity data that we've assessed. And it also serves as a tool for predicting hazards for specific ecosystems. So let's say you're in charge of managing risks of microplastics in your freshwater lake, and you know the types of species that are in your freshwater lake. They may be species that are of commercial importance, or they may even be species that are endangered, or certain organisms that you really want to protect more than others, that sort of thing. So using the Tomex database, what we can do is actually derive species or ecosystem specific thresholds that are bespoke to the particles in your environment. And I don't know if the it looks like the preview that I tried to show is actually not showing, maybe because it's a video. But if you want to check out the Tomex, I can send you the link in the chat as well. Something that we're doing with this database right now is updating the database to ensure that it includes data that has been published since our working group closed its doors back in 2022. So for aquatic organisms, we added 125 studies, and for human studies, we added about 50. This more than doubles the size of these databases and makes them a lot more usable for folks that are trying to predict risks in ecosystems and in humans. So I want to talk briefly about what we've actually done with this data, with the hazard levels that we've derived. And one of our principal collaborators, Bart Coleman's, was able to use this data to assess risks of microplastics in the Laurentian Great Lakes. And this is really a fantastic case study in how to apply these methodology for freshwater environments. And so real briefly, what they found was that in sediment, there's likely risk of microplastics already occurring in Lake Huron. And that's based on the impacts due to food dilution, as well as translocation mediated impacts. Luckily, in Lake Ontario, they found much lower concentrations of microplastics, and they predict that risk is unlikely. And when it came to surface waters, in both Lake Ontario and Lake Michigan, they found that risk was likely for microplastics at the current observed levels. So this is certainly worrying, as it is the first reliable indication of risks in a freshwater environment in the United States. In terms of monitoring going forward, if I were a lake manager, I would really focus my efforts on monitoring in sediments, because this is where we see the biggest sink for these particles, especially when we're looking at the variability across time and in space. Particles in the water column are highly variable. They can shift around with a moment's notice. But once they reach the sediment, they're much more immobile. So it makes it just a lot easier to actually monitor and get reliable data. We also see that from a recent study in Rhode Island, the closer your lake is, or the closer your water body is to an urban environment, the more likely you are to have contamination. So we also applied this risk assessment framework to San Francisco Bay, and we characterized the ecological risks based on what was in the floating water column. We collected particles using what's called a mantitrol, as shown in the picture. So looking overall at the samples and the thresholds that they corresponded to, we found that the majority of samples in the San Francisco Bay already exceeded our risk thresholds for that corresponded to performing additional monitoring. There were some samples that were very high and exceeded our least conservative thresholds for doing management planning as well as source control measures. Luckily, most of the samples outside of San Francisco Bay were below all of our thresholds, indicating that there's some accumulation happening in the bay. We also assessed the uncertainty around this assessment, and we found that there are very high uncertainties when you look at the rescaling and alignment procedures that we had to perform in order to make these comparisons more reliable. And so because we have such a high uncertainty with this risk assessment, we're not applying a 3 or 3D listing. Instead, we are taking a more soft regulatory approach, and we're doing what's called a 305B listing, or category 3 under the integrated report. So we're basically indicating that there's not enough information to determine beneficial use support, but there is information that indicates that beneficial uses may be threatened. So really all we're saying here is that we should probably perform more monitoring in San Francisco Bay. We also characterized what was driving the uncertainty in our assessment, and it was mostly due to the fibers that were the high variability in fiber data that we're getting from these manotrols. And one of the ways that we can deal with that is to use what's called in situ pumps, where we're pumping a very large amount of water in the water column. And this will hopefully capture these microfibers in a more reliable way than dragging a manotrol through the net, through the water, excuse me. So in terms of what to do with all this information from a management perspective, we have a plan for testing of microplastics in drinking water for 4 years. And this was adopted in 2002 under the policy handbook shown here. And one of the things to understand with this approach is that most water treatment utilities are already filtering out microplastics that can be seen with our methods. Flocculation and sedimentation gets out most of the particles down to about 1 micron or so. And unfortunately for us, that's below the size that we can reliably detect with these methods. Also, we're really most concerned about the particles that are smaller than 10 microns for human health. So in order to make use of these imperfect methods in this scenario, we're applying a principle known as rescaling to understand the particle distribution that we'd see below our size limits of detection. This is very similar to, if you know the shape of an iceberg and you can only measure the bit that's above the water, then you could interpolate the amount that's below the water. So we adopted this iterative monitoring approach for drinking water back in 2022. Just a real brief overview here. We're going to start monitoring in California summer 2025. And there'll just be about 28 water systems that are involved. And they'll be looking for water mostly in surface water reservoirs, as well as in the California State Water Project, the Colorado River, a few other strategic areas. And then in 2027, we'll reevaluate the state of the science and see if we can look for microplastics in additional systems, whether it might make sense to adopt newer methods that can look for smaller particles in the treated drinking water. We're trying to spread out the monitoring across the state, and a lot of these monitoring locations may also be good indicators of general contamination in the environment. So they may be useful also for freshwater lake managers as well, especially if the lake is also used as a reservoir. I'm going to skip over a bit of slides because I just want to make sure that we have enough time to talk on really what our big next steps are going to be. One of the main types of microplastics that we're worried about moving forward are microfibers. We're seeing a large increase in the number of microfibers that are being produced globally. It's mostly polyester clothing, and it's going not only into water bodies, but also into the terrestrial environment through the application of biosolids. And so what happens when you buy your apparel and you wash it in your washing machine is that hundreds of thousands of microfibers are coming off from each load. And those are being sent to a wastewater treatment plant where they capture most of those microfibers into the biosolids. And in California, we use biosolids for land application, for farming, as well as other applications. And so a very large amount of microplastics are being sent to California's agricultural fields on an annual basis. About 75% of biosolids in California are land applied, which comes out to 723,000 dry metric tons approximately each year. So one of the ways that we can deal with this is by capturing the microfibers in washing machine filters. And there's a bill going through California's legislature that would actually require all new washing machines to have a built-in filter for microfibers. So we'll see what happens with that going forward. Um, Benjamin, I just want to make sure that we have enough time for Q&A. So we've got 10 minutes until 1. Do we want to like wrap it up and just ask if anyone has any questions?
We can reserve, I don't know, if you have any, like maybe 5 more minutes, we can kind of split the middle. But yeah, I think, depending on how much more time you have or how much more content you have, let's keep going.
Okay, cool. Yeah, I'll just wrap it up. So just want to give you an idea of what the state is doing to tackle this issue from a holistic view. I mentioned before that we've got this requirement to address microplastics in the marine environment. And in 2022, we adopted a statewide microplastics strategy. It's a 2-track approach where we're taking no regrets solutions today, including pollution prevention, dealing with pathways that we already know are problematic, and doing outreach and education. And then the second track is conducting additional science to inform future actions. And so this really involves updating the science in real time, as I've been showing you. I like the work that we've been doing. We also understand that as time goes on and we emit more plastic into the environment, ocean risks are going to be increasing and may likely be irreversible. So it's really important that we take a precautionary approach when applicable to prevent potential irreversible impacts to the global marine environment. And so one of the ways that we're doing that is really just thinking about upstream impacts. How can we prevent plastic from getting into the environment in the first place? And really the best way to do that is to simply not make it. There's a lot of different ways that our legislature is dealing with that. The next best thing is to prevent it from getting into the environment through proper waste infrastructure and also capturing it in locations that make sense, such as wastewater treatment plants, stormwater outflows, rivers. And the last resort is trying to clean it up out of the ocean. It's extremely expensive and may cause a lot of harm along the way. So we really have to think about this issue as more than just a waste problem in order to have these upstream solutions. And this is something that the California legislature has taken on in a very ambitious way, thinking about a circular economy and extended producer responsibility framework. 2022 saw the passing of the Comprehensive Packaging Extended Producer Responsibility Bill, Senate Bill 54. This has got to be the most ambitious plastic extended producer responsibility bill in the United States, and maybe one of the most ambitious ones in the world, because it requires that anyone selling plastic, single-use plastic in California, verifies that it's actually being composted or recycled. And they have to meet certain targets by certain years. Otherwise, they get hit with fairly significant fines. And so 65% is the target for 2032. And we are also requiring that these organizations contribute $5 billion over 10 years for the impacts that they've already made to the environment. Let's see. I'm just going to wrap it up. I want to make sure that you all have a way of getting involved further in this research community if you so desire. I run what's called the Microplastics Monitoring Subcommittee of the California Water Quality Monitoring Council. And this is a local and global community exchange of information and data for microplastics monitoring methods and tools. And we entertain some pretty incredible guest speakers every quarter. We also have working groups that are developing a sampling and analysis playbook to assist anyone that we doing monitoring. We developed a communication toolbox for water systems to communicate risks of microplastics to their consumers. And we also have a work group that talks about laboratory accreditation and data analysis. So if you want to join our next meeting, it'll be on July 11th from 1 to 3. So I can drop a link in the chat as well if you want to get the email list of updates from that. So I want to thank you all for your attention. I can answer questions for these last 5 minutes. And apologies again for the technical errors that we had.
Yeah, thanks, Scott. If anyone has any questions, feel free to ask now or type it in the chat. Well, I'll start off with a question, I guess. So this week we saw that the EPA had released some guidelines for PFAS in drinking water systems. Is there any sort of correlation between PFAS and microplastics?
That's a good question. So there is a little bit of overlap in terms of co-contamination. Some plastics are coated with PFAS, but in general, we actually don't find a whole lot of PFAS on microplastics. Really, the biggest concordance between these two contaminant suites is the complexity. And PFAS is as complex, if not slightly more complex than microplastics in terms of dealing with the issue. And so I'm ambitious, or I'm hopeful that EPA tackling a very complex, diverse contaminant suite like PFAS will pave the way for smarter approaches for dealing with microplastics as well.
Great. Okay, we got another question from Aaron. Does silicone present similar or same risks as plastics, especially with respect to cooking?
That is a great question. So silicone-based plastics are also considered microplastics at the small scale. We have not seen research that suggests lower toxicity from silicone microplastics than other types of plastics, carbon-based plastics. There's a bit of a packaging greenwashing that goes on. Some silicone producers actually say that it's plastic free, but by the legal definition that we've adopted and by all the research, it really is plastic. We should be skeptical of its use.
Okay. Another person asked, Aaron asks, I assume the research on the biological detox pathways is still lacking?
By that, I assume that you mean the elimination rates for plastics from organisms. We have a fairly good idea about the accumulation rates in marine organisms, fish and other organisms. We know how much is going in and how much is going out. We don't have a good idea for humans. We're starting to get some biomonitoring data of what we're seeing in feces and urine, as well as what's in our blood, and that's really the data that will be necessary to understand elimination. So, yes, we don't have a whole lot of information for that.
Okay. Manjeet asks, is there any real monitoring system, Ben, or to be considered in future to alarm agencies?
I'm not entirely sure. Real time. Oh, real time. Okay. Um, in terms of real time monitoring for microplastics, there are a couple. There are sensors that use computer vision and cameras to look at particles in a water stream or water sample, and using machine learning, they can figure out which ones are likely plastic and which aren't. But those are not really going to be useful for drinking water plants because we're looking at much smaller particles that can't really be seen even with a microscope. Um, and in terms of real-time monitoring in the environment, um, those might have a limited application. So um, I would follow up with that because there may be new developments that happen.
All right, thanks. All right, well, I got one more question. So you mentioned earlier about the microfibers basically entering landfill or some sort of compost. What's the risk of these entering the food system?
That's a really good question, and one of the biggest inquiries in the field right now. We know that plants uptake microplastics through their roots and that they can distribute them through the shoots as well as into the edible portions of their plants. We've seen several reliable papers that show that with increasing levels of microplastics, plants grow slower and eventually will not grow at all. So it's unclear if this is a relevant exposure route for humans yet, because we're not really monitoring in food, but we do know that eventually it may impact our food sustainability and agricultural output.
Wow. All right, well, that seems to be a time. Unless there's any last minute questions, I want I want to thank you personally for doing this. It's again, we had your talk about a year or two ago, and that really opened my eyes, and that's why I wanted to invite you over again. And again, it's the emerging threats of microplastics are very concerning, and we're glad that we have people like yourself researching it and being the liaison to the public. So thank you very much.
Awesome. Thank you so much for inviting me. It's great to meet with you all.
All right. You all have the good rest of your afternoon, and stay tuned for our next webinar next month. Thanks.
Thank you.